Okay, last time we started talking about continuous symmetry, and I had a really rough argument for the existence of a lower critical dimension at d equals 2. So what we're going to do now is put that on more firm footing by doing it properly in terms of a field theory in the continuum. So what I want to do is look at the divergence of the integrals in that continuum expression. Just like we did for the upper critical dimension, this is how we'll define the lower critical dimension for the continuous case. I want to derive the nonlinear sigma model and do the RG for it. So we'll do a type of epsilon expansion for what's called the nonlinear sigma model, except I'll be skipping most of the details because I think we've already done one detailed calculation. So I'll work through that today and Friday. Next week we're going to take off for the March meeting. Then I want to come back. I want to talk about the Kossuth-Salas transition, which will take a class or two. And I'll probably finish on sort of an RG. We'll do an application for the last 1 or 2 classes, which will be an RG calculation of entanglement entropy scaling, which I think is something fun. So we're wrapping up. We only have a few things left to cover. And I guess we have 6 lectures to do it, so we should be in pretty good shape. Okay, so to derive the nonlinear sigma model, you'll see it different ways in different books. But I'm going to just start with the functional or the action that you guys have already looked at on your assignment. So we're going to start from sort of a known point. So the spins, or the degrees of freedom, are the object of continuous symmetry. They'll have n components. Okay, so if there were just one component, they'd be the scalar theory. 2 components we'll call the O2 model, 3, O3, or Heisenberg, and so on. So this is the ON theory. So the spins have components, and also remember, space has components. So when you write the action for these vectors, so that's your vector field with n components. Remember, there's a d-dimensional integral over space. And that's the d that you set, to 2 or 3, say, 1, 2, or 3. With an upper critical dimension. So I'm going to write this like component-wise. And I'll explain this in a minute. I'll do it like this. Okay, so you've seen or you've argued or you've derived something like that before. So just keep in mind here, what do I mean by this? You might also write this like, say this, for example. So once I get sloppy, I'll start doing that. And all this is a sum over components. So here I have a repeated index, A from 1 to n. Right, the components of your spin. But then I also have a gradient term over all dimensions, d. So it's partial field component, like that. Okay, so just keep track of the fact that there's 2 quantities there. Okay, so the first thing I'm going to do is take this field this vector component field, and write it as a magnitude and a direction. So remember, there's a spatial dependence, right? The fields are a function. This is a functional, because every field is a function of x. So in space, in d-dimensional space, I can define the field as having a direction and a magnitude. So I could call it that. And I'll call it magnitude and direction, n. And of course I leave out all that spatial dependence, but that's the point of the field theory, right? Is the order parameter, if you will, is represented by that object which varies in space. And this thing will be a unit vector. So it just specifies the direction of the field. And that n being a unit vector gives us all the important constraints, sort of, when we derive the nonlinear sigma model. Okay, so let's rewrite the Landau theory, or the action, in terms of rho and n. Okay, so we just look at the important pieces. So for a single component, we have a magnitude, and then our vector component is translated to the unit vector. So that's a term we have to calculate. And so the first term in the action is this thing squared. Which I'll write like this. Right, squared. Good. And let's see, 2 times right. So I'm repeating indices. So then this is just the dot product here. Okay, so the constraint on the length gives you unity for that. I have a term here that's the vector component and a gradient, which should be orthogonal, I think, so this should be 0. So I just have these 2 pieces. So my action is a function of rho and n. Okay, so the sort of, rho squared and rho 4 part look the same as in your scalar theory. And the big difference in this continuum theory is these gradient pieces here. But when we spoke about mean field theory, or we did the saddle point approximation early on, fluctuations always raise the energy anyway. Right? So the mean field solution to this, or any action of this type, is when the field is uniform in space. So if it's uniform in space, then there's no gradient, and those first two terms drop out, and then our action is just the same as the 5-4 theory that we've already solved. So that's the mean field theory solution, which you guys argued for on an assignment. So then S is like a free energy in the Landau theory, which is just dependent on rho. Also, I'll just write it like this. And you know what this looks like. We can draw it for, say, the two-component case. Hello. So you can imagine looking at the free energy or the functional for R positive, which will be like a parabola. Oops. That's spun around the x and y axes. I don't know. Right? With a minimum at 0. And then when R is less than 0, we're looking for the minimum of the free energy. So if we set the derivative, then we can write this as either minus R over U, or magnitude R over U. So that's the solution to which looks something like this, with a minimum for O2, that's like a circle there, and here. Okay, so the point is that below the phase transition, even though the magnitude rho is fixed, basically the angle around that, this potential minimum, the angle around that circle doesn't result in any raising in energy. So unlike the Ising model, for any of these ON models, there's no energy barrier to global rotations of the field. Remember, everything's uniform in the mean field theory. So you picked an arbitrary direction somehow. But there's no energy cost to a global rotation of all those spins, as long as there's no gradient between them. And that's the same as going, from this position to this position in the direction of n, defined by n. Okay, so even in this mean field type solution, because there's no energy barrier or free energy barrier for rotation, then you expect those fluctuations to be very strong. Okay? So even as you cool down to essentially 0 temperature, you'll get fluctuations around the minimum of that, they call it Mexican hat potential. I think it's racist. But the bottom of this well, like I say, even down to 0 temperature. So any theory of this, ON model at low temperature has to include those, if you will, transverse fluctuations of the order parameter. And far below the mean field transition, this rho is like your magnetization. So far below the transition point, that rho is essentially fixed. Okay, so let's consider fluctuations around this mean field solution. Okay, so we're going to begin with the order parameter that's essentially fixed in magnitude, like this, and we're going to consider how to include fluctuations, in this global direction n. Let's say around. Okay, so write the magnitude of the order parameter. Choosing a direction for the, for the mean field solution that we're going to look at fluctuations around. And so we'll just define that n component vector such that, because it's a unit vector, we'll just pick the direction, or we'll define the direction of the first component as the direction of that vector. Then a field at any arbitrary position in space will be made up of the mean field, okay, rho n vector. But now I want to include fluctuations past the mean field. And I'll write it like this: delta phi. And let's call it perpendicular. That should be a vector. So it's like the fluctuations in all these different directions that are 0. And this will be what I use to define fluctuations. It's the same as the mean field plus fluctuations for the scalar theory. I've just broken it into these two pieces. Defines fluctuations. Delta. And I should break those fluctuations into, no, I'm going to keep a fluctuation transverse and parallel. So I'll just write it like that, and then I'll break it up. Yeah. And I'll have a 1 component plus the transverse component. So that allows me to reduce the magnitude of that 1 over there. So this is parallel. This is transverse. Yeah, good. So then this thing, since it's transverse, has a 1 component that's here. So it's not in this vector. And then everything else is, say, 2, 3, all the way up to small n. So later what I'm going to do is I'm going to redefine this notation a bit. I'm going to define my unit vector n as sigma and pi's. So later I'll have sigma, pi 1, pi 2, pi n. So it's just a little bit of a parameterization difference. So when you define the nonlinear sigma model, this is how this unit vector is parameterized. So there's a relationship between these, but let's just talk in terms of mean field plus fluctuations, since that's how we framed things originally for the scalar theory. Okay, so we take this, same thing we did, I don't know, months ago, and we plug that into the action. Okay, and we expand out terms. So let me start doing that. And like before, we'll leave terms up to second order in the fluctuations. Okay, so I need so what do I want to do here? Let's go back to that first action I wrote, just to keep everything clear. So I have terms, I got phi dot phi squared, then I got the gradient terms. Okay, so term by term. Good, so I'll pull out the magnitude, rho squared out front. Then I just have n and the fluctuation squared. N dot n is 1. Guess I need a dot product here. And then I have the fluctuation dot product. All right. So let's further break this up into parallel and transverse. Right. All right, so then I'll have 2 parallel plus the fluctuation. And then I should have the transverse dot product. Transverse dot product. Good. Okay, we'll leave it at that. Then we need phi dot phi squared. Okay, so that's like the phi, that's like the equivalent of the phi 4 term up here, with coefficient u over 4. And let's only keep, again, up to order, second order in fluctuation. So let me just write out what this turns out to be. Can you check this? Actually, you can get it right from here. So you have 1. So you're squaring this thing, right? And then this term times that term. And now the delta phi 1 squares, we get, 2 plus 4. So that should be 6. So it's 4 plus 6. Delta phi 1 squared. Okay, and we're throwing away higher order terms. And then we have this twice. So it's 2 delta phi delta phi. Right. Okay, so we've thrown away everything higher. Okay, so that's r by 2, u by 4. And now let's do the gradient terms from this 1/2 gradient terms right up there. And I'll write them with this repeated index notation. I guess you still need the dot product for the, because each one of these is a vector, even though we were going component by component, right? Mm-hmm. Okay, so let's write these out. So okay, so that's parallel and transverse. Mm-hmm. Okay. So all of my dependence on that, I have gradients of a vector. You know that n is fixed. So those gradients are going to fall out. So what I'll end up with is so that's, you know, in this approximation, those gradients fall out, but in the nonlinear sigma model, when the next step where I'm going to refine this a little bit more, then you're going to have to keep those gradients. So that's this. And perpendicular. Mm-hmm. Good. So now all we have to do is we collect the terms in here, right, in here, and in here. So we have those three terms. Each term has a coefficient. Also, this is rho squared. Also keep that in mind, rho 4 rho squared. We have coefficients, r over u. But we can also substitute in the mean field solution for rho, which relates r over u. So with those ingredients, we can simplify this action. Okay, so let's just keep looking at this. Okay, so we got 1/2 in front of here, so it's rho squared by 2. Okay, that's the first term. That's the coupling in front of the second term. And we need the U. And this is all. So use a mean field solution for the magnitude of the order parameter. So we square that here. Power 4 there. So let's look at some of these terms. There's two that should vanish. I think it's this one. So let's look at this term, which occurs here and here. Right. So the coefficient of that term so let's see, it's R rho squared plus U rho 4. This is 2 and 4. So it's minus R squared over U. Right. Yeah, so that one cancels. And so should the other transverse piece. So I think it's this one here. 6, 4. No. No, they got to be factors of 2. Oh, yeah. It's got to be this one then. So it's got to be this one. This is a factor of 2 different, right? Okay, so both those terms disappear. Okay, so we need the one I scrubbed out, delta phi 1. We just need the coefficient of that term. So I'll call it rho squared magnitude R. Okay, I've just plugged in the mean field solution for rho. Good. So now our action, which was an action for phi only seems to have the fluctuation left in it. Also, let's just write the fluctuation piece. Looks like I forgot a fluctuation piece right here, right? Mm-hmm. Delta fluctuation phi. Okay. And what is it? Rho squared. 2. I can write this like 2r phi 1 squared. Good. So this is the correct sort of mathematical picture of those things I just erased in some sense. Because now you're looking at gradients of fluctuations in different directions, right? So if you fluctuate the order, the direction here, so see that thing's defined as being parallel, then it costs you some energy here. All right, this term, the magnitude of this fluctuation matters in terms of your action or your free energy. But here it's only the gradients that matter. So this is the term, this is like the fluctuation term that would appear in the scalar theory in some sense. Call it n is the direction. So remember, the fluctuations I'm talking about in those pictures are uniform, right? Because you have a dot product there. So it's uniform deviations of the direction. So I just put in math what we already had in that figure that was right here that I erased. But we can use this expression to derive the lower critical dimension now. So let's just take this action and look at almost the same way we did for the upper critical dimension. Let's just look at it in Fourier space. So we'll transform the fields and look at the properties of the integrals as a function of dimension d. So what we need to do is define the fluctuations in K space. So that's just done through the Fourier transform. Let's do a discrete sum. So this defines delta phi 1 K. And we can do the same type of definition for the transverse component. Do component by component. A, K. I forget which one of these has. Oh no, these are both. Yeah, so there's no minus. Never mind. ED I K X.
Can I ask about meaning of energy cost?
Meaning of what?
Energy cost. So
Yeah, I'm being loose with that.
you concluded that there's no energy cost to the perpendicular to that.
Yeah, so in the saddle point approximation, right, Z is e to the minus S, this S, right? So then that's the interpretation of that is basically free energy. So if you're at low temperature, say, then the only component of your free energy is your energy. So at very low temperature, then it's only an energy cost. But you could also say free energy. Yeah.
Then still, the gradient of the perpendicular component appears in the integrand, right?
The gradient of the
Perpendicular component.
The perpendicular component. Yeah, so you have the dot product of the gradients, yeah.
Then how can we,
So that'll be some value, and you're rotating that thing uniformly. So it has to still be uniform.
so that's nothing to do with the energy cost in the perpendicular direction?
So that term doesn't change, I think. Is that right? If you uniformly rotate the definition. So it could be there. That term could be finite, but it just doesn't change with a global rotation. That's what I mean.
When you say global rotation, do you mean an active or a passive transformation?
I have no idea what that means.
Okay, well, passive transformation would be a gauge transformation. You just change the way you look at it. An active one would be you're looking at the energy cost of physically rotating it. And I'm looking at that and thinking, well, if I'm doing that globally, isn't there going to be a locality issue which will force domain walls and then there'll be an energy cost?
I'm going to say no.
This is another example of mean field theory not caring about distance.
I mean, the mean field solution is a uniform field in the thermodynamic limit. So it's a global rotation of that field uniformly. So domain walls mean it wouldn't be uniform. You know, there's no features at all in space.
Global rotation, that's a non-local operation. No, it's a thermodynamic limit. I've got a lattice which is infinite, and I'm saying I'm rotating a field at once, and I'm actually doing that. I'm not just changing my coordinate system. Right, that's a non-local operation.
Okay. I don't think it matters. Okay, so in Fourier space, I'm writing it as sums. Okay, I'm not going to do, so remember, let's see, when we have a gradient, right, that's like a derivative. So it brings down from the exponential a k, because you're taking the derivative of that thing. So for every derivative term, we have a k squared. And this just means the Fourier transform. You have two of these exponentials. Let's see, right? And by definition, the delta function. Then you have phi 1k, phi 1 minus k. I could write it out. I'll write out. Well, I want to fit this on the board. Anyway, it's the same thing we defined before. We have 2r delta phi 1 K. I'll write like that. Okay, so what I mean is, here's the other K term. K squared. So this one will be minus K. That's all I mean by that. Okay, so I could have written this as delta phi A perp K magnitude, or whatever you call that, norm. Okay, so once you do these 4H transfers a few times, you just find the gradient terms, put K's. Don't forget your volume if you want to be precise. So now in K space, you can look at this energy cost. So again, it's free energy. I'm just calling it an energy cost. If you have delta phi 1, so if you have a fluctuation, right, in the field, then that'll cost you energy for any K. But the energy cost for both of these terms go to 0 as K goes to 0. So that's another way to look at it.
Then can I say, if having the perpendicular fluctuation doesn't make any energy cost, but if that variation is depending on position, then that can cause energy cost, right? Yeah, so this is a statement of K equals, this is what you see here. It has to be K equals 0 for these things to not cost energy. But yeah, that statement's correct. That's what we'll do. We'll start to work on that next. So I like this view in K space. Because you just look at these terms and ask what they mean. So if that thing's finite, so is always perp K So in the long wavelength limit, so when K gets very small, so when the momentum gets very small, then the fluctuations are free. They don't cost any energy. So that's one definition of the Goldstone modes. So these say things. So it's like you're talking about if that position-dependent fluctuation. So is the dependence of that position. So say they're pretty much right. So if there's uniform rotations, then those don't cost you any energy, right? But you can also have very long wavelength fluctuations that span, the entire lattice, say. And those will be your lowest order deviations, like your lowest order energetic excitations. So these are no excitations. They cost you 0 energy. Something that has a very long wavelength, whatever, that's the wavelength. So that wavelength's very long. then that's the lowest energy excitation that you'll see in that type of action. So those very low energy excitations are, they're called, they would be the Goldstone bosons in the quantum version of this. Okay, so zero modes and very low energy long wavelength modes. And because, why long wavelength? It's because of the K dependence of this stuff. So Goldstone modes, they're physical. You see them experimentally. They occur in any system with a continuous symmetry. Spin waves. Magnons, Hillary, to answer your question from yesterday. These are what magnons are. They're long wavelength spin excitation in the ferromagnet. Phonons, lattice vibrations, quantized lattice vibrations. Those are basically Goldstone modes. I can't think of anything else off the top of my head. Quantized, what is it? Lattice vibration. So just say lattice vibration. Okay, so we don't do it here, but basically quantizing this long wavelength excitation is what gives you a boson. So Goldstone modes are bosonic in the quantum theory. Let's just look, I want to look at the correlation function.
So, Roger, I have a quick question. So, you're doing classical physics, right?
Yep.
And in a sense, we don't need the quantum physics for these to make sense, right? I mean,
No.
yeah.
I'm just saying,
Okay.
when you have a long wavelength excitation
like
in a continuum system.
I can also see these sort of like Goldstone modes.
Yeah, so completely classically, there you have a Goldstone mode. That's why I didn't write boson on the board.
Oh, okay.
Yeah, so this is all classical. I'm just saying
Sure.
it's bosonic in the quantum case. You just have to, you just got to treat your momentum as a quantum object, and then you see why. Yeah, so this is completely classical. Okay, so let me look at, in order to see the lower critical dimension, I'm still chasing that. Let's look at the 2-point function. Right, so I want to look at the transverse and parallel modes. So let me call them G1 and G perp. Okay, so I have fields that can fluctuate. So I want to look at these as a function of distance between x and x1 and x2, x and x prime, say. We've already basically done this type of calculation, so we just have to look at that action and think about what it gives us. Okay, so there's my definition of a 2-point function. It's the correlation between fluctuations between x and x prime. That's what that delta means, remember? So I'm x prime. I'm asking how fluctuations in the field. So that might be my direction n. You know. I have a fluctuation here, and my n's the same. And I have a fluctuation here. So I'm asking how those fluctuations are correlated. Okay, so that's in real space. Let me just Fourier transform this. Turns into k and minus k, remember? And e to the minus I. No, plus I. And I can do this similar thing for G perp. Okay, so I need to take that Gaussian expectation value, where that expectation value is defined with respect to this action here. Okay, so we have the same type of, we got these two gradient terms. So that's my k squared term. But only in one case do I have a massive term. Does that make sense what I just said? So in only one case do I have this piece that has that r, which is again the parameter that changes sign to the phase transition. So you already can see what these correlation functions are going to look like just by looking at this. This, when r is finite, you know, just think of your Landau theory. This means you're either above or below the transition. And we're assuming we're below the transition, basically. In this term, for the perpendicular term for fluctuations, it's like there's no mass term, so it's like you're at a critical point. It's like your r, if there was an r perp, that r perp is 0. Okay, so we can just basically write down what these expectation values are. Or if you don't believe me, you can do it. Let me just keep track of mine. So I got a V. I got a rho. So I'm going to have a V over rho squared. A V squared here. And then I have K in both cases. But here I have the, whatever you want to call it, the mass. And here, so again, after the Fourier transform, the big difference is this term is 0, so it's just 1 over k squared. So again, this one looks off critical. This one looks critical. Because it's like you've tuned the action. So that's essentially the answer. So in real space, Okay, you solved these things before. So the dominant term here, because it's like you're away from criticality, I can write it like this. For my correlation length, it's 1 over 2r. And in this case, it's like I'm critical. So instead of the exponent being the dominant piece, this is only the dominant piece. You also have a 1 over r d minus 2. That's what dominates here. D minus 2. Let's forget about the anomalous dimension. So it's like the correlation length just to the Goldstone modes is infinite. So let's just calculate that 2-point function for the Goldstone modes explicitly, okay? And if we solve that integral as a function of dimension, this is what I'm chasing for the lower critical dimension. So I hope this works. Those things are vectors, so let me be more careful. Mean that's what that 2-point function means. It's like the mean squared fluctuation, right, of the order parameter due to the Goldstone modes. Oh yeah, so it's mean squared. Let me just set x equals to x prime. Yeah, that'll give me the mean squared error. So instead of the 2-point function, I just bring them together, calculating that component-wise. So it's like my x minus x prime is 0. And I got repeated indices, but G, yeah, 0. Okay, that's like the mean squared error, mean squared fluctuations. So this should be so I have an integral. I have to integrate over that 1 over k squared. And that sum goes from like the second component of the vector to n. So it's like n minus 1. Yeah, so I should have something like this. Okay, I'm going to change the sum to an integral, which sucks that volume in, that v over there. Okay, let me do that explicitly. If I do it in my head, I'll screw up. So I have a sum. Yeah, so if it's 1 over v, yeah, so then I'm set. I can define a cutoff. in K-space. I feel like we've done integrals like this before. So let's pull out the surface area of the sphere, of the unit sphere in K-space. Call that SD. Pull out that 2 pi. So let's see, now I have k to the d minus 1 dk over k squared. Okay, that worked. It's a miracle. So these are fluctuations. So we've calculated an integral that tells us the strength of fluctuations. So it's dimensional dependent, just like we had with the upper critical dimension, right? It's dimensional dependent. So when d is greater than 2, so when d is 3, 4, 5, 6, then that integral converges. And if it's, less than or equal to 2, then it diverges. So that means the fluctuations are either finite, they're either convergent, because that integral is just some constant, or that integral blows up, and that means the fluctuations blow up, and they're constrained by the size of the ON vector anyway. But so that's why 2 is playing a critical role for divergence there. Fluctuations blow up, it means the fluctuations become more important than the actual order itself. So those fluctuations proliferate, then you can expect no long-range order. T equals 0, okay, well, why is it t equals 0? I'm assuming basically that the magnitude of the order parameter is fixed. And all I'm looking at is, so when that's true, then, even though these things don't cost any energy, so there's 0 energy, they can only live at t equals 0. Or they still live at t equals 0, let me put it that way. If you raise the temperature, then you also have to worry about longitudinal fluctuations, delta phi 1. So in that case, you would have to also be a little more careful, but this is another way of looking at the Mermin-Wagner theorem. Just considering what that integral means. In what, D, say less than, So 2, that integral also has problems at 2, right? So that's why 2 is the lower critical dimension there. So that really rough, all we've done is really like refine that really rough argument I had last class. And here we see what the mechanism for the Mermin-Wagner theorem is, what's causing a divergence that kills the order. So this, we boiled down to basically this thing, which is the Goldstone modes. Okay? Does that make sense? Questions?
So if you look at the formula for G perpendicular
Mm-hmm.
x minus x prime, so the absolute x minus x prime to the power of b minus 2. So if it's a 0, it's already divergent. So is it consistent?
Yeah, so if it's 1 over something to the 0, then that's not divergent.
But if d is greater than 2,
So d is greater than 2.
yeah, still it's in the denominator. So
Sure.
denominator is 0.
Sure.
It
So in that
will
case,
drop.
yeah,
Is it
yeah.
consistent with this conclusion?
Let's see, what does it mean? The correlation length. I mean, the correlation length can only be infinite. It can only be up to the size of your cutoff. So you know that x minus x prime can only be of the order L. So
You obtain the mean square fluctuation by summing of the G perpendicular 0, right?
yeah. So that sum doesn't matter. All it is it's setting this to 0. You're looking on site, right? Yeah. Yeah. So okay. Yeah. So in that case, I guess this one clearly shows you that 2. You know, if you plug 2 into there, you get 1 over k. So it's the same expression. You just integrated it. Other questions?
So in principle, the parallel component and the perpendicular, they're not independent, right?
Yeah, so that's what we're going to do next class.
Oh.
So this was sort of order 1, or maybe mean field theory is order 0, and this is order 1, treatment of fluctuations. So now what I want to do is be more careful and look. I'm going to look near the lower critical dimension and define that n vector. Remember, it's sigma pi 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 pi. And so this is what defines a nonlinear sigma model. Is you're more careful with that constraint, basically, the constraint on that unit vector. So when you have fluctuations in the transverse direction, then they decrease the magnitude of your vector in the ordered direction. Okay, I was going to start today, but why? Let's start next class. So that's what we'll do. We'll drive the nonlinear sigma model, and I'll look at we'll do the momentum shell RG and derive the RG recursion relations for that. I don't know if I can do that all next class. We'll see what happens. And then next week, I'm going to the March meeting, so let's cancel class. And then after that, we have 2 weeks left. So all I want to do is finish up Causa's Salus and do that entanglement calculation. So
Both classes are cancelled.
yeah, cancel both. Cool.